Last topic of the chapter is about binary operations. First of all, we need to know the meaning of the words binary and operations. Binary generally means two, so it should always occur in either one or only two ways only. So, what is operation? Operation is some task that are going to do with the numbers. Because it's maths, we are going to do with the numbers only here. So generally a general form of a binary operation, let me call star as a binary operation. And how do I define this? Star on set A such that, so you need to write like this, it is from the set of A cross A to A. So you need to get generally a binary operation by simple meaning. You can understand that it is maybe some two numbers that is belonging to this set X. This is the input, and this you are going to get an output, say some other number C in X that is present in the same set X. This is called as a binary operation. So simple binary operation could be addition. Addition, I will denote it as a plus sign as for the binary operation, that is on the set of real numbers I am just taking here. So it is from R cross R to R. So let me take any number, say 1 plus 2. So it is 3. So 3 is also belonging to the real numbers. So if I take any number like half into half, so this will become 1 by 4. 1 by 4 is also real number. So it is belonging to this. What do you call? This is the set of real numbers. So if I take the negative sign and maybe I am giving like this, or I can write, I'll change the set now. Let it be Z into Z, Z cross Z into 2Z. So it is only the set of integers. It's the meaning the same. So if I take any number, so from the set of integers, I will take the number 5, and for this Z, I will take another number, say minus 3. Right? I need to do such that A minus B. Right? Star shows star, or with respect to this it is a negative. So A minus B, A is 5 here, B is minus 3. 5 minus of minus 3, that is equal to 8. So 8 also belongs to this Z. That should belong to that Z. That is called as a binary operation. Right? So we'll just check one more. That is, for example, I'm going to take the multiplication as one more binary operation. By multiplication for a binary operation, let me take the set of natural numbers n cross n to n. Right? So let me take any two numbers from this. One of the natural numbers is 4. Another natural number from this set is 6. So the operation says that you need to multiply both the numbers. So I need to do 4 into 6 in this case. This is into, not the cross one. So this is 4 into 6 is equal to 24. 24 also belongs to this set n. That's why this is also an operation that you are applying across the two numbers, that is 4 and 6. Right? Now we'll see some more examples so that we get it clear what is the meaning of the words binary operations. Okay? Here we are going to learn how to denote a binary operation just for learning. Say star is an binary operation. This is star. This generally are denoting it like this. So if it is a number like A star B, yeah, I'm considering this as a binary function in this case. So if I write A star B, this is the function that is going to be taking place. So if it is a addition, so A star B is same as A plus B. Right? If I consider the star function to be the subtraction, that becomes A minus B. If I consider the star function should be of multiplication, this becomes AB. That's what the meaning, how to denote this. Right? This is the function. This is the way of denoting based on the given this is the binary operation. So let us have some examples to check whether it is a binary operation or not. So the thing to check the whether it is a binary operation or not, for that we need to check whether this right hand side belongs to the same set. So for example, let me take subtraction in natural numbers. Subtraction in natural numbers. So the function, not the function, it is a binary operation. Binary operation minus, that is represented like this, from the set of natural numbers, Cartesian product of the set of natural numbers to the set of natural numbers. So let me take some number out of this. So let me take A and B. So let A be 1 and B be 3, right? So what does this minus? Minus is a binary operation which says if you take two numbers A and B, A minus B is the right hand side. Yeah, after operating with that you get A minus B. That's what the meaning of this. So what is A minus B? A minus B is 1 minus 3 in this case, right? 1 minus 3 is minus 2. But minus 2 is not a natural number, right? So you can say that by taking this example, it is not a binary operation in this case. That's why since minus 2 is not belonging to this, you cannot say that this is a binary operation. If it is belonging to that set, say if I take the integers, then it belongs to this, right? That time you can tell that it is a binary operation. Similarly, you can also tell that division in the natural numbers is also not a binary operation because it has some other exceptions. If I take the same two numbers, it becomes A by B, right? For division, it becomes A by B. If I take 1 and 3 again here, this comes to be 1 by 3. 1 by 3 is a fraction and it comes only under the rational numbers. Until that it doesn't arise at all. Even in the integers it doesn't arise. So you need to get the rational numbers for that. So here in this case, natural number for division also is not a binary operation in this case. Okay. Now we'll go to some of the properties of binary operations. Properties of binary operations. The first, we need to know that binary operation is just a special case of a function, right? In a function, you have, say you tell that this f is a function that is from the set R to R. Yeah. Similarly, here also you are telling that star is a binary operation that is from the set R cross R to R. The difference between these two is that the both of them are tending to the same one, but the left hand, here you are opting from the Cartesian product, but here you are opting only from that set the elements. So the first thing is about this is operation table. How do you draw the operation table for a binary operation? So let me take a binary operation. Say star is a binary operation from the set of natural numbers. So it is, you have to denote it like this. And what does it say? It says that star is such that it is the LCM of A and B. So how do we draw the operation table of this? So let me take only the numbers from 1 to 5. So you need to draw the operation table. So you need to write like this: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and draw the lines. Right? You need to draw the lines because it's a table. You need to draw the lines like this. Okay. After drawing the lines, you need to fill up all this. Here, this is the A, and this is B. Yeah, LCM of A and B you need to find out in each case and fill in those boxes. That is what you're tasked to do. So LCM of 1 and 1 comes to be 1. LCM of 2 and 1 is 2. 3 and 1 is 3. 4 and 1 is 4. 5 and 1 is 5. Similarly, you'll get here also, because this is, even if you interchange this B and A, this is not going to make much of a difference. So this, you're getting 2, 3, 4, 5 in this case, right? So if you take two numbers, always if you get the same numbers again here, say AA, its LCM will be A itself. So if you are taking two numbers 2 and 2, its LCM will be 2 itself, right? Similarly, you will get 3, 4, 5. That's how I filled this much now. So I need to take care of these two now. This is 3 star 2. LCM of 3 and 2. That comes to be 6. So this is also same because it's the opposite. LCM of 2 and 3 is 6 itself. Right? So next we'll come here. LCM of 4 and 2. LCM of 4 and 2 is 4. That's you are getting 4. So here also I'll get one 4 here. So LCM of 4 and 3. Let me fill this. 4 and 3 is 12. So this is also 12. Because they do not have highest common, their highest common factor is 1. That's why their LCM comes to be 4 into 3 itself, 12. So now here 5 into 2, both are prime numbers, right? So their LCM will be their product itself. Right? Here one more you have. Both are prime numbers, no problem. Again go on multiplying, it comes to be 5, 10, 15, 20. 15, 20. Just you need to take care that this is 5 itself, not 25, because 5 and 5 is the same. Their LCM comes to be the same number. This is what you draw as the operation table. This continues on both sides because it is from n cross n to n, right? So we'll go to the next topic. The second property we have of the binary operations is of commutativity. Commutativity. You might have heard this word in some other chapters, maybe in the very young, maybe primary. In 6th standard or 7th standard, you might have learned what is the commutative property of the addition of two numbers in natural numbers and real numbers and such things. So commutativity of this binary operation. So what does it mean? Star is a binary operation. Star is commutative only if A star B is equal to B star A for every A comma B that is belonging to this set. So we may say maybe the set I am considering on set X, say this is on set X. So then A comma B also should be belonging to that set. So let me explain once more. So commutativity of the binary operation can be shown if you use that operation interchangingly, you should get the same value for every values A and B that is belonging to that set from which you are opting, right? So let me take some example. Say star is a binary operations in the real numbers itself. Leave the real numbers, okay? So what does it say? You can say that A star B is equal to AB by 4. Okay, 2 let it be. AB by 2. So now I need to check whether it is commutative. For checking whether it is commutative, I need to just generally check this statement is true or not. So what does LHS say? LHS is equal to A star B. A star B is equal to A into B divided by 2. Right? What is the RHS here? RHS is equal to B star A. Right? In the first place I need to write B here. Second place I need to write the A. Wherever A is there, you need to write B, because B is first here, not A star B. This is B star A. So B should be written first. That is B into A divided by 2. So just by properties of multiplication, you know that AB by 2 and BA by 2 is same, right? Therefore, star is commutative in this case. Star is commutative. Right, let me take one more example. Say, let me rub this. Have you seen this? Okay. Let me rub this. Oh, all these things let be the same. So I need to give one example for which it is not commutative. Right? So for that I'll take an example. Say A star B is equal to A plus 2B. A plus 2B. Okay, this is a simple addition, but in this case you have one 2B here. That makes a difference whether it is commutative or not. So A star B is A plus 2B. B star A is, in place of A, B comes. In place of B, A comes. So this is B plus 2A. Are A plus 2B and B plus 2A equal? No, they cannot be equal. So they can be equal only if B is equal to A. So, but for this, here you considered that for every A and B that is belonging to X. So, I think you know this notation. This is saying for every A and B that is belonging to that set X. So, here in this case, so some example I can take, say a number, let A is equal to 1 and B is equal to 2. So A star B or 1 star 2 is equal to 1 plus 2 into 2, or 1 plus 2 into 2 is 4, comes to be 5. Then what is B star A? B star A or 2 star 1, 2 star 1 is 2 is first, right? So A, the first number is coming as A here, that comes 2 plus 2 into B is 1. B is 1, right? So 1 here. That it becomes 2A plus 2, that is 4. So from this example you can just say that 5 is not equal to 4, that is already known. So A star B is not equal to B star A. Hence, therefore, star is not commutative in this case. Star is not commutative. Okay? This is the second property of the binary operations. There is one more similar property that is going to come under binary operations, is the third one. So generally it's the association property that comes, that is going to be bringing here. So the third one is the association. Generally when you talk about association, it's coming together of 2-3 things like that. Association, or I can write it as it's the property, right? It's associative or associativity, I can call it. So let me have a star is a binary operation on set X, right? That is belonging to, so if I have A star B star C, see, if I write this as A star B star C, what can you understand from this? It's a binary operation, so you need to take only 2 at a time. Which 2 I should take as first here? You just come under a confusion in this case. So when you generally write 3 like that, you need to write like this, or B star C, right? A star and B star C. That is what the meaning. Because only 2 can be taken at a time for a binary operation, because it's a binary, only 2. That's what the meaning. So if I have like this is the meaning of the associative property. So if you have a bracket A star B into a star C is equal to A star into B star C. Okay, for every A, B, C that is belonging to this set X, right? I took the set X here. So I should give an example now. Let me take the example to be example. So let me take some other shape. Okay, this is some shapeless. Okay, we just consider this. I think you have learned about this in the mathematical reasoning in last year, I think. This is the function you have now. So star is a function such that you are applying it on A and B, then A star A, this thing, up arrow into B is equal to AB by 3. Okay, AB by 3. This is similar one as the previous one. I took AB by 2 there, here is AB by 3. This is similar one. So I need to take LHS and RHS to just prove. So LHS is A star B into star C. That is equal to, what does this come in this case? First you need to take only these 2 now. Forget about C. So what is coming inside the bracket is only bothering at the first step, because it is in the bracket. So AB by 3, it is the same, right? I need to take this one in this case, right? Not the same there. So this is the function, binary operation. So this becomes AB by 3, because you are applying to A and B in this case. So this is one number now. AB by 3 becomes one number and C is one more number, or whatever, rational, real number. So AB by 3 is one number and C is one number. So in place of A, I need to write AB by 3. AB by 3 is one number and C is one more number. right? In place of A, I should write this whole term, that is AB by 3. In place of B, I should write C, because that is the order in which they have occurred here. Right? Now I need to write one more 3 here, because the function binary operation says like that. So what does this become? This becomes A, B, C divided by 9. So let me fastly calculate now. So A, B and C, that comes to be now first here you have to be going inside the bracket here. So A and B, this one B and C comes to be BC by 3, that is equal to, now this is the first number, this is the second number, so this is A into BC by 3 divided by 3. Right? Now again we'll get the same number, that is ABC divided by 9. From this you can just conclude that this both are equal, right? Those both are equal, that's why this binary operation is an associative. So I need to also show you one more that shows no associativity, right? Let me take the same example that I have taken in the previous one. So maybe I'm more comfortable with star. I got confused this time, right? So let me star itself. Star as A star B is equal to A plus 2B. I think this was the previous one. That one I showed that it is not commutative. This is not associative also. I can just prove that, right? So the first one is A star B star C. A star B star C. So A and B first you need to apply. That comes to be A plus 2B and star C. Okay, this is not okay. Let me bracket one more. This is the star function. So this is a star binary operation. This is the first number. This is the second number. In place of A, you need to write the first number. That comes to be A plus 2B, and this is the second number. That is 2 times the second number. That is 2C plus 2C. Right? So next I'll take the right hand side. It comes to be A star B star C. That is A, I need to remain it like this. B and C becomes B plus 2C. Okay, this is the first number, this is the second number. Here B is first, C is the second. So it becomes B plus 2C as the second. This is one. So this is the first number, this is the second number in the next case, because here is a star. So for that, the first number I need to just write it as it is, and the second number it becomes 2 times B plus 2C. That becomes A plus 2B plus 4C, because 2 into 2, that is 4C, right? So just by seeing that you can understand that only A plus 2B is common, and there is one 4C, that is here it is 2C. So just by seeing that you can conclude that it's not associative for the given set of, say if I take this real number as a set, so this you can just say that it's not associative, right? We'll go to the next property. Okay, now we have the third property of the binary operations, that is of identity. Okay, not third, I think fourth, right? Fourth property, that is of identity. What is the identity of a binary operation? So let me consider star as a binary operation in this case. So if star is a binary operation on set X, so this is the set X now on which you are going to have the binary operation. So let me name E as identity E. So let me take an element A in this case. So A star E should be equal to A, that is equal to E star A for every A that is belonging to X. So what does this mean? Let me take some example and explain, right? So before that I'll just explain what is given in this question. Sorry, the property. This is A star E, that should be equal to the value, right? So in a function, in a binary operation, you have say R cross R to R, right? So if this first and second are A and E, and you get A, that should be the first condition. The second condition should be that A should be equal to E star A, or here you need to consider E and here you need to consider A. You should get the value of A after applying the binary operation. Okay, so now we'll take an example. Say plus is the binary operation. What is plus? This is the addition. So A plus B, it is going to be the thing. So the first one is A plus E. So let me find the value of identity of the for addition. That is additive identity, that is called. So A plus E is equal to A. That is the first one. Second part is, so this is the second part, that is E plus A is equal to also A. Right? I should cancel here. I can find in both the cases that E is equal to 0. Hence I can conclude that 0 is the additive identity. Okay, let me take multiplication and also find out the multiplicative identity. We already know that multiplicative identity is 1, but I need to just show how the procedure goes on. So star is a operation such that A star B is equal to A into B. Okay, so the first one is A star E. You need to find out E here, right? That should be equal to A. So that is A into E, right? AE is equal to A. So A and A is going to be cancelled. So E is equal to 1. So if you just get in the first case, it's not enough, because you have two conditions in this case. So it should satisfy both the conditions in this case. So this is E star A is equal to A. That's also should be possible here. So that becomes E into A is equal to A. A and A will get cancelled. You get E is equal to 1. Since you get E is equal to 1 in both the cases, you can just conclude that E is 1 is the identity for this given operation. Here the operation is multiplication. So we can just tell that it is a multiplicative identity. So let me take some other numbers, some other operation. So one more thing you need to take care here, that every operation, binary operation, doesn't have a identity say a number. So if I take some other operation like A plus 2B is a number, is an operation that stands for A star B. A star B for an operation, binary operation star. This is the operation here. So I need to get two numbers like this. So I'll just try if I can get such like something like that. So the first number is A and second number is B in the first case. That is A star E is equal to A. This is the first condition. I can just assume whether I can get here. So A star E comes to be A plus 2B. That is A plus 2E is equal to A. So A and A cancel. You get 2E is equal to 0. Therefore E is also equal to 0. I just skip that step. So the second part shows that E star A is equal to A. Okay. Then applying this, that is A plus 2B. A is E here. First number. The second number is A here. So it becomes 2A. 2A is equal to A. So I need to transpose here, or what do you call that, transform here. That is E is equal to minus A. A minus 2A comes to be minus A. In this case, you found out that in E in both the two cases are different. So therefore no identity exists, because it needs to satisfy both of them. But here it is not going to satisfy. Here one kind of number is satisfying that condition, another number is satisfying another condition. Therefore that given binary operation doesn't have an identity. Okay. So I need to add one more line based on what I found out here. So star on set X has identity E for the operation. Okay, operation that's not required, right? Then if it exists, that is the most important part of this. If it exists, because in this case you found out that it does not exist. So the star and set X has an identity if exists only if A star E is equal to A is equal to E star A. This is the important thing that you need to remember. Generally 6 mark questions come under to find out whether it is commutative, associative, identity, and also find the inverse. That is the next part of this properties. Okay. The fifth property of the binary operations is to check whether it is invertible. So in the functions, you found out how to find invertible. Here you need to find for binary operations. So how do you check whether it is invertible? So there are only some elements of this binary operation that can be invertible, and not all of them. And many times none of them are invertible. So let me just tell the definition of what is an invertible binary operation. So if you consider a star, so that should have some identity element, right? Star is a binary function with the identity element E, right? In the previous one we found out that we could denote it by E, right? So this identity element E, for which you're having that previous one, that is A star E is equal to A, that is equal to E star A for every A that is belonging to that set. Say on set X, I am considering in this case. So this much you found out. So it can be invertible if it is having an element E, identity elements with respect to the operation, right? And that E should also belonging to the X, right? That was what we understood in the previous one. E should be belonging to X. That is invertible. So after finding that it is invertible, we can just tell that some of the elements of this binary function can be having an inverse. What is an inverse in this case? So what is an inverse? So let me just write the definitions of how it should be. So if it should be having an inverse, say A has an inverse, then A star B is equal to E is equal to B star A, right? This is a combination of two conditions that, as we understood in the previous one also, here you have A star B is equal to E and B star A also should be equal to E. That's what this. Then B is equal to, or B is the inverse of A. Then B is the inverse of A, inverse of small a, if, so I'm considering the set as X itself. So, and A and B should be belonging to X. That is the condition. E, A and B should be belonging to that given set also. Then B is the inverse of the that given element of this binary operation, or you can element of that set, right? Yeah. So how can you denote that? In the previous one we denoted identity function should be E. Here you need to denote the inverse of A. So I can just write it as B is equal to A inverse. This is the inverse function, not 1A. So generally we mistaken it for, maybe I am at 5 raised to minus 1. So using the law of exponents I can write it as 1 by 5. But this is not true in this case, not always, because in the law of exponents you can use that, but here it is not the meaning the same, right? So that's what you need to learn about inverse of this. So now we have the inverse. So let me take one example. Let me write here a simple example like an addition. Addition is about A plus B, right? So E we found out to be 0, right, in the previous part of the lesson. So A plus B. So this should be the condition, right? A star B is equal to E is equal to B star E. So A plus B is equal to 0 is equal to B plus A. This is the first case and this is the second case. So A plus B is equal to 0 or B is equal to minus A. So you know the term A in both the cases, and you are asked to find the inverse of A in this case. So for understanding that, I've just written this as B here, right? Let B be the inverse of the given, say, an element A. So just I'm going to explain that. So this is the first condition, second condition. Similarly, you have B plus A is equal to 0, and therefore B is equal to minus A. So in both the cases you have confirmed that minus A is the inverse of A in the given case. That becomes therefore minus A is the inverse of A. That's what you found out. So this is true only if it is considering the set of real numbers or integers or any other thing like that. So if I consider plus is a binary operation that is from the set of natural numbers, the Cartesian product to the set of natural numbers. So in such a case, minus a will not exist. Minus a will not exist. So in this one, you found out that a and b should be belonging to that given set. Here the given set I am considering in this case is a set of natural numbers. So you find out that minus a is not belonging to that set. So you can just tell that a doesn't have an inverse in that case, right? In this case, none of them have their inverse. None of them have inverses. That's what to find out. Okay? That's it. Next we are going to the exercise based on the binary operations. The first question of the exercise 1.4 is to determine whether the given binary operation, that is star, is a binary operation or not. Right? Here is some given operation. So you need to just check whether it is a binary operation or not. So for the conditions to satisfy the binary operation, you need to just know that all of them, similar to a function, each of them should have a unique image over there, and that is the main thing over there, nothing else. So first, this is subtraction, right? Same as subtraction, and you have the z plus. What is z plus? All the positive integers, that is excluding 0, 1, 2, 3, 4. That comes to be the natural numbers, right? So you have all of them here. Okay, instead of this, yeah, all others are z plus, or that is equal to the set of natural numbers. So you need to have an image. So if I have a and b, let a is equal to 1 and b is equal to 3. So a minus b is equal to minus 2. That is not belonging to n or z plus. Therefore, this is not a binary operation. That is one of the counter examples to just prove that it is not a binary operation. Okay. Next one is AB. AB is this multiplication. Multiplication is a binary operation in the set of natural numbers also. So this is AB square, that is A into B square. So it is a similar to multiplication, A and square of the second number. So similar to multiplication, right? So it is a binary operation. And it is a real number. There is no problem at all. So now you have the modulus sign of A minus B, right? So let me take the same example to check whether it is. So I'm feeling doubtful about this. Yeah. Okay, I'm going to say the same example. So it comes to be modulus of A minus B. A is equal to 1 and B is equal to 3. That becomes 1 minus 3. Modulus of minus 2. It comes to be 2. But 2 belongs to that, right? 2 belongs to z plus. Therefore, this is also a binary operation. This is just one of the examples. Just you can understand that the modulus sign shows that only a positive integer is going to come, because a and b are also integers. Inside this modulus sign, whatever it is, as a result you will get only a positive, non-negative. Sometimes you can get 0 also in this case, I think. Alright, so it's okay. Now you have z plus and a. Right, if you are given two numbers a and b, after applying the first number is a, right? Whatever, what is the problem in this? It is a binary operation. Okay, now we are going to have the second question. Yeah, now we have the second question. The second question is to just check whether it is a binary operation, whether it is commutative, whether it is associative for the given functions. I have written only first 5. Sixth one I am going to do in the later part. So the first one is a similar one. So this is the set of integers and this is subtraction. So it is a binary operation because all the numbers are included within that. So it is going to be a binary operation. It is commutative or not. So just by saying that a minus b is not equal to b minus a, they are not equal, right? So it is not commutative, right? If now we are going to associative property is a minus of b minus c should be equal to A minus B minus C. That is A minus B minus C, or when I take minus inside, this becomes A minus B plus C. You can just see that they are not equal, right? So there, it is not associative. Right, now we are going to the second question. Q stands for the rational numbers. So now we have the rational numbers with us. So this is simple multiplication, A into B. 1 is just added as every number, so leave that 1. To just check whether it's a binary operation, it's just a multiplication, A into B. Hence it comes to be binary operation. Yes. Yeah, now we go to commutative property. So for commutative property, it should be A star B is equal to AB plus 1. A star B is equal to A into B plus 1. Okay. Then what is the right hand side? That is B star A. B star A is B into A plus 1. B into A plus 1. 1 is common. A into B, A into B. This is equal. Right? Therefore it is commutative. So now we need to check whether it is associative. That is A star of B star C should be equal to A star B into star C. Okay. So now what is B star C? B star C is B into C plus 1. B into C plus 1 is equal to A star B is AB plus 1 star C. So this comes to be A into BC plus 1 plus 1. This is the first number, this is second number. So first into second plus 1. The same thing I am going to do here. First into second, that is AB plus 1 into C plus 1. 1 and 1 will get cancelled, or leave it without cancelling. Generally, while showing the stepwise, you need to do LHS and RHS separate. This is just for your understanding, that's why I am doing both of them together here. So this comes to be ABC plus A plus 1. Okay, I have not cancelled 1 here. And RHS you have ABC plus C plus 1. So you have ABC and 1 in common, but you have A here and C here. So this shows that it is not associative. It is not associative. Now we are going to the second part. Third part, you have the set of rational numbers with AB by 2. AB by 2. This example I have shown already. I have written the question to be AB by 2, AB by 3 and all. While showing the examples for commutativity and associativity, I have already explained during the explanation of that. Now we'll go to the fourth part. This is Z plus. Z plus stands for all the non-negative integers. So 2 raised to AB. It is a binary operation. Okay, it is a binary operation. Now we have a commutative property. For commutative property, leave this 2 part. The operation between these two numbers is just by multiplication. So it is commutative. Since multiplication is commutative, this is also commutative. So I'll just explain how it is. 2 raised to AB is A star B. What is B star A? 2 raised to BA. Right? B and AB is the same. Right? This is just simple multiplication. That's what I'm telling. So now we'll go to associative property. That is A star B star C. So what do you get here in the left hand side? So A is first, right? So A, you need to leave A and you need to write 2 raised to BC. Okay. Now this is the first number, this is second number. So you need to write 2 raised to, first number is A into 2 raised to BC. Right? This is the number you are going to get. Just leave it like this. It is very difficult to simplify and all. So now we have next part is A star B star C. What is A star B? Is 2 raised to AB. 2 raised to AB star C. So this is the first number, this is second number. 2 raised to first number into the second number. Just by comparing, you can understand that these both are not same. Here you have A and BC. Here you have AB and C. There are some other wrong things, so they cannot be associative. Okay. Now we have the last out of this, and you have one more, I think. I have not written here. So the first part is just to tell that it is a binary operation. Just by seeing you can understand it is a binary operation, because integer raised to an integer is also an integer. Always it comes to under an integer, and since a and b both are positive, their power also, the number also comes to be positive. That's why it is under binary operations only. Next we have to see whether it is commutative. So for it to be commutative, a star b should be equal to b star a. A star b is equal to a raised to b. What is b star a? B star a is b raised to a. They are not equal, therefore it is not commutative. Now we'll go to the associative property. A star b star c is not equal to, I have to just check, right? And a star b star c. So we will take a out, a is remaining outside, b and c, that become b raised to c. B raised to c is one number, a is one number, so I need to take a raised to b raised to c, right? A raised to b raised to c is the number you are going to get. Here you have a star b. A star b is a raised to b star c. Here this is the first number, this is the second number. First number should be down and second number should be the exponent. So a raised to b raised to c, that comes to be a raised to bc. Here it is b raised to c and here is b into c in the exponent part. Just check the exponent part. The exponent part, here it is b raised to c and here it comes to be bc. So they are not equal, right? So it is not associative. The sixth question is from the set R minus 1 a by b plus 1. So just seeing this minus 1, you can tell that the denominator cannot be 0, right? Just by seeing that. So this is similar to leaving this plus 1. A by b is similar to division. Division is an operation, right? So this is also a binary operation. So next part is commutative. So we need to check whether it is commutative. A by b plus 1 should be equal to b by a plus 1. Is it equal? No, it cannot be equal. But it is not commutative. This is a star b and this is b star a. So the next part is a star b star c and a star, okay, a is in the common, right? B star c. First a, then b and c, right? So it is b by c plus 1. First divided by second plus 1. Similar here also, a by b plus 1 star c. Then now again first divided by second plus 1. Here also you have the first is this one divided by second plus 1. Here you have a by, you are going to take here and a becomes 1 plus c, and this is LCM, right? So it becomes b plus 1 times c plus 1, that is c plus 1 itself. This is the left hand side. Right hand side is a into c plus 1 divided by b plus 1. Because this is a numerator and this is a denominator, so denominator of the denominator goes to the numerator. So this becomes a into c plus 1 divided by b plus 1. See, you can see that in both of them the numerators are the same but the denominators are not matching. Here it is b plus c plus 1, there is one more extra. Here you have only b plus 1, so you can just tell that it is not associative, right? Now we go to the third question. The third question is just to write an operation table of the given operation. What is the operation given over there? The binary operation star given in the third question is all about how you need to find a minimum of two numbers, right? So the third question, minimum of a and b. So you are selecting two numbers. So the given set here is from 1 to 5. The number is from 1, 2, 3, 4 and 5 are the 5 numbers here. So and the operation is like this that I had used in the one of the things. So this is an operation. So you have 5 elements here, right? So 1, 2, 3, 4, 5. Here I am not going to draw the lines and all, so it will become dirty otherwise. Okay. So now you have, this is A. A is, okay, anyhow, let me take, this is A and this is B. This A is horizontal and B is a vertical one. So I'll just draw one line only here. Okay. So now you have 1 and 1. Minimum out of 1 and 1 is 1. Minimum out of 2 and 1 comes to be 1 only. Right? Minimum of 3 and 1 is 1. 1, 1. Because you have only 1 in this column. So next we have here. Similarly, you have 1 here and all the numbers are greater than 1. So all the remaining also comes to be 1 here. Okay. Next we'll go to the second column. Second column is about 2. So second row is all about 2. Second column is also all about 2. So minimum out of 2 and 2 is only 2. Minimum out of 3 and 2 is 2. So similarly you are going to get 2, 2, 2, 2, 2. Okay. Next you have third column and third row with 3. So 3, minimum out of 3 and 3 is 3. Minimum out of 4 and 3 is 3. And again 5 and 3 is 3. Again here also you get the same. Okay. Next you have 4 and 4 is 4. Minimum out of 4 and 4. Minimum out of 5 and 4 is again 4. Again 4 and 5 is again 4. And the last one comes to be 5. Because minimum of 5 and 5 is 5. This is the operation table for the given operation. Okay. This is the operation table. Next question. Let us continue with the exercise now. We have our fourth question from the exercise 1.4. Here star is a given binary operation on this set. This set is having elements 1, 2, 3, 4, 5. And this is how the operation table goes on with this. This is the operation table with the elements 1 to 5. Okay. So let me take this as A and this is B for my convenience to just understand how it is. So the first part of the question is to compute these two values. This is 2 star 3 star 4. So first I need to compute 2 star 3. That is 2 star 3. That comes to me 1. So this becomes 1 star 4. Okay. Now we have to take 1 and go to the fourth column. Fourth column is 1 again. So this is 1 here. So now we have 2 star 3 star 4. So this is to be computed first. 3 star 4. This is star, right? This is 4, right? This is similar to the multiplication table that we have written. So this comes to be 2 star 1. So again 2 star 1. You're coming to the first column here. This becomes 1 as a value. So 1 is the value. In both the cases you get that 1 is the value. So the next part of the question is to check whether it is commutative. So just by seeing the operation table, one simple method is to just draw diagonal like this. Maybe you need to draw a diagonal like this. So if it is symmetric along that axis, that means that, so you can understand that here too, here also 2 is present. The second part of the question is to check whether it is commutative. The simple method of finding whether it is commutative is to draw a line here like this. This is a diagonal passing through this given operation. So if you draw a line like this, it should be symmetric along this axis. So here it is 1 1 1 1 1 1 1 1 1 1 2 2 1 1 1 1 1 1 1 1. You can see that. So this, you can say that even if you interchange A and B, you are going to get the same operation. Therefore it is commutative. The third part of this question is to compute this value, that is 2 star 3 star 4 star 5. 2 star 3 comes to 1. This is 1 star. Now you have 4 star 5. 4 star 5 comes to be again 1. 1 star 1 is 1. So this value is 1 here. So now the fifth question is to just prove that the fourth question, the given star in the fourth question is the operation of the HCF of two numbers based on the set 1, 2, 3, 4, 5. You need to just show that you're going to get the same table in the question 5 also. That's it. Okay, that is the given binary operation. Next, we'll move on to the sixth question. Now we have the sixth question of exercise 1.4. So the question is the binary operation star, which stands for the LCM of the two numbers to which it is applied. The first part of the question is to find 5 star 7. 5 star 7, based on this given star as the binary operation, this stands for LCM of 5 and 7. Since both 5 and 7 are prime numbers, their LCM has to be their product. That will be equal to 5 into 7 or 35. Okay. Now you have 20 and 16, and you need to find the LCM of 20 and 16. This you can see that they are not prime numbers. I know that 20 is equal to 5 into 4 and 16 is equal to 4 into 4. So the LCM will become 80. Because 1 4 is repeated, I am excluding that. So here 4 and 4 becomes 16. 16 into 5 is 80. So this comes to be 80. I hope you know how to find the LCM also. It should be commutative. So what does it mean? A star B should be equal to B star A. This stands for LCM of A and B. LCM of A and B. And this also stands for LCM of B and A. Okay? That means both are equal. That is, it is commutative. Associative. For being associative, what is the condition? For being associative, it is like A star B star C should be equal to A star B star C. Okay? So now when you apply, you get LCM of A and B star C. Then again, when you apply this, you get the LCM of A, B, C. Similarly, you'll get for the right hand side also. From that you can infer that the given operation, that is the lowest common multiple operation, is associative in nature. Okay? So now we need to find the identity in the set of natural numbers. Here also you need to find invertible elements from the set of natural numbers. So first we need to find the identity. Let the identity be E. So A star E should be equal to A. That should be equal to E star A. Okay? Let me take two numbers. LCM of A and E is equal to A. That means that E is a factor of A. Therefore, E is a factor of A. Similarly, you get LCM of E and A is equal to A. You will come to the same conclusion in both the cases. Since E is a factor of A and A is every general number, so if E is a factor of every number, that means that E is equal to 1. That is the meaning of E is a factor of every natural number in this case. Therefore, the identity in natural numbers is 1. Okay? Next should be, you need to find the invertible elements. What is the meaning of to find invertible elements? So let me rub this. Right? So we have two elements, say A and B. That should be equal to E here, and B star A. That is, LCM of A and B should be equal to E. E in this case is 1. So I'll replace this E with 1. And this also should be equal to LCM of B and A. Okay? So by saying this, you can understand that this and this is equal. So I'll just rub off this condition. You have only one condition in this case. So LCM of two numbers is 1. If LCM of two numbers is 1, both the natural numbers should be equal to 1. Therefore, the only invertible element is 1, and inverse of 1 is equal to 1. This is the notation of inverse. So you need to find the inverse of 1. By saying this both are 1, that means that B is the inverse of A, right? So when A is 1, B is also 1. Okay? So that is the only one case in which you can find the invertible elements. Next we are going to the 7th question. Here we have the 7th and 8th question of exercise 1.4. The 7th question is about a star that is same as LCM as the previous one, but here the set is set 1, 2, 3, 4, 5. The question is to find whether this is a binary operation or not. So for a binary operation, every of those elements should be having okay, let me name this as set A. So the star should be from set A cross A to A. Okay, so let me take one example, say 4 star 5. 4 star 5 stands for LCM of 4 and 5. LCM of 4 and 5, these two are co-prime numbers, therefore their LCM comes to be their product, that is 20. But 20 does not belong to the set A. See here, your set A has only 1, 2, 3, 4, 5. But 20 should belong to the set A if it is a binary operation. Therefore, star is not a binary operation. Okay, now we are going to the next question. Or just before that, once more I'll explain what is it. This is the domain, or this cross Cartesian product is the domain, and this set comes to be the codomain if you consider this as a function. Okay, so if you are taking 4 star 5, you are going to get 20 in this case, but that 20 does not belong to this set A, so therefore it is not perfectly a function. Or in other words, this is a binary operation. If it has to be a binary operation, the output after operation should be belonging to the same set, but this does not belong to that same set. That's why this is not a binary operation. The next part, the 8th question, is about HCF. Here you had LCM, this is HCF. HCF, I think you had already done the 5th question. So the first part is just to check whether it is commutative. For that it should be A star B and B star A. A star B is a HCF of A and B, and this is HCF of B and A. However, whatever order you take, both of them are coming to be equal, therefore it is commutative. Okay, now we are going to have the third associative part. You need to check whether it is associative. And this is A star B star C and A star B star C. This comes to be A star HCF of B and C, and this comes to be HCF of A and B star C. Okay, so at last you are going to get this as HCF of A, B, C, and this also you are going to get the same. Therefore it's equal, so this is associative. Next you have identity. Identity is how A star E should be equal to A is equal to E star A. These two conditions should be satisfied. Okay, so now take the first condition. So E is considered to be the identity element. You need to write that. Let E be the identity element. Okay, now you have some arbitrary elements. So if it is HCF of A and B, that means that this is HCF of A and E is equal to A. This comes to be the same, right? So those two conditions sum up to this condition only. Only one condition is obtained here. That is HCF of two numbers is A. That means that E is a factor of A. Since A is every number in the natural set of natural numbers, E can be only 1 because 1 is a factor of every natural number. That's why, therefore, E is equal to 1. Since A belongs to N. That's why the identity element of this binary operation, that is HCF, is equal to 1. Now we have the 9th question. 9th question is all about to find whether it is commutative and associative or not. So just I made a table so that it's easy for us to see. So the first part is to find A minus B. Note that the given set is set of rational numbers. Okay, rational numbers. So this is the set making of subtraction. So A minus B cannot be B minus A. This question is similar to the second question, first subdivision, where it is just asked, but the set given over there is all about integer. Here it is about rational numbers. That's it. That you can just show that it is not commutative, not associative. This is a square plus b square. A square plus b square stands for the operation here. So if it is commutative, a star b and b star a should be equal. So what is a star b comes to be a square plus b square. What is b star a comes to be b square plus a square. Both are equal, therefore it is commutative. Now what is it to be associative? To check whether it is associative, we need to take that part. This is the bracket part and all. So this is a star b star c and a star b star c. Okay. So first I need to do this. This becomes a square plus b square is one number now, and c. So what is this? It's all about square of first term plus square of the second term. That is a square plus b square whole square plus c square is the output of this. Okay. Now we'll take this one. This is a star b star c. So b star c should be done first. So that comes to be star of first square plus second square. So first is b square plus c square. That comes to be one number now. Now again you are going to do first square plus second square, b square plus c square whole square. So from this you can tell that a raised to 4 plus b raised to 4 plus c square plus the 2ab term comes here. That is 2 into a square into b square. A square b square is the extra term you are going to get. Here you are going to get is a square plus b raised to 4 plus c raised to 4 plus 2b square c square. Okay. Just by comparing, you have a raised to 4 here. Here you have a square. B raised to 4 is okay. Let it be. There it is. This is c square and c raised to 4. You have a square b square term and you have b square c square term. That means that this is not associative. We can give some example and just tell it is not associative also. So now the third subdivision is about a into a plus ab. Okay, a plus ab. So just by looking that I can take out a as common outside here, I can redefine the function to be a into 1 plus b. Right? This is the same. If you multiply now, we'll get a plus ab. That's a binary operation here. So now what you're going to do is to find whether it is commutative. That is a star b. A star b is a into 1 plus b. That is what is given here. Then what is b star a? B star a comes to be b into 1 plus a. Just when you make it big, this becomes a plus ab. This is b plus ab. Even though ab is common, here you have a, here you have b. Therefore, when a and b are not equal, this cannot be equal. This sum cannot be equal. Therefore, it is not commutative. Now to check whether it is associative. To check whether it is associative, you need to have this condition, right? B star b star c. So this is first now. This becomes a into 1 plus b is one number star c. Then first number into 1 plus second number. That is a into 1 plus b into 1 plus c. That's what. See, first number into 1 plus second number. That is first number into 1 plus second number. That is the first one. Here you get a star. That is first number into 1 plus second number. Okay. Again you are going to do this. This first, this is second. First into 1 plus second number. Just by observing, you can find that these are the three factors for this one. But this is not a factor, proper factor. I can just expand it to be 1 plus b plus bc. This is a into 1 plus bc plus b plus c. Just by expanding, you found that there is one c extra term in this case, but it is not there over there, right? So you can tell that it is not associative. Now the next part is a minus b whole square. For making it commutative, since it is a square, directly you can tell that it is commutative, but I'll just explain that. A star b and b star a. This is a minus b whole square. That's how it is defined here, right? So now the second part is b minus a whole square. b minus a whole square. So if I am taking a minus sign inside a square, it doesn't make any difference. See, this becomes minus, I'll take inside a bracket, this becomes a minus of a minus b whole square. Now this is minus 1 square into a minus b whole square. Minus 1 square comes to be 1, that is a minus b whole square. So these both are equal, right? Therefore it is commutative. How to show it is associative or not? Most probably it is not associative because it is so complex. It becomes. So the first one is a star b star c, that is a minus b whole square star c. So what is the function is first minus second whole square. Now the first number is a minus b whole square, first minus second the whole square. Okay. Now the second part is a star b star c, that is a star first minus second whole square, that is b minus c whole square. Again you are going to do the same, that is first minus second is b minus c whole square. Okay, first minus second the whole square. Just by observing, you have a c term, but here you don't have a c term. Here you have an a term, here no a term is present. From that you can just conclude that it is not associative. This is commutative as well as associative. You can just refer to the question, second question, third subdivision. There the question was AB by 2, here is AB by 4. That's it. Because it is just a simple multiplication as a binary operation, this comes to be both commutative as well as associative. Okay, we'll go to the last point, that is the sixth one. This doesn't look like it's commutative also. So a star b and b star a, this comes to be a b square, that is first into second one square, a into b square, then here first into second square, b a square. Are they equal? They're not equal, so it's not commutative. Now we're going to the second part, that is a star b star c, that's a b square star c. So first into second square, that is ab square c square. Okay, that is the first one. Second one is a star b star c, that is first into second square, a star b c square, first into second. This is first, this is second in this case. So now again you are going to do first into second square, a into bc square whole square, that comes to be a b square c raised to 4. Here you have c square, here you have c raised to 4. That is the only difference over here. That means that it is not associative. Okay. Next we are going to move on to the 10th question. Now we have the 10th question. 10th question is also based on the 9th question. We are all these 6 subdivisions. In the question it is asked whether any of them have an identity element. Okay. For having an identity element, what is the condition? If E is the identity element, let me consider E is the identity element, then A star E should be equal to E star A, that is equal to A. That is the condition. That's a set of two conditions over there. So, but just by seeing these two, that this is equal to this, I can rule out the non-commutative ones, because this just shows that it is commutative, right? So I can rule out that first, third and sixth cannot have an element at all, identity element at all. So now we need to just check third, fourth and second, fourth and fifth. So now we'll go to this one first. So let me take only one condition so that I can get whether it is proper. E star A is also equal to E. Okay. So star function, here the star operation says first one square plus second square, that is A square plus E square is equal to A. And here also A square plus E square is equal to A. Both conditions are same here because it's commutative, right? So I can just remove one condition, right, from starting itself. Okay, this A square plus E square is equal to A. But here you do not get a proper condition, that is E square is equal to A minus A square, and you get some absurd result and nothing else. So you can just tell that there is no identity for the second one also. Okay. So now we'll go to the fourth one is one that is commutative out of the others. Fourth one says a minus b whole square is equal to, is the operation, that is here it comes to be a minus e whole square is equal to a. I'll expand this comes to be a square minus 2ae plus e square is equal to a, right? But still I am not going to get a particular result of e over here, so let me get that result. So if I need to get the result of e what it is, then all the a should get cancelled and e should be just remaining with some numbers, maybe an integer or a rational number. Here it's the rational number, right? So it needs to come at the rational number. So this you need to stop at that result because it's going to be too complicated things and you need to get e out of this. So it's almost very irritating. So just leave it. So it is not going to have an identity element in this case also. So we'll go to the fifth one. Fifth one is ab by 4, that is a e by 4 is equal to a. Here a is going to get cancelled. So e comes to be 4. Therefore e has an identity element and the fifth one has an identity element, that is e, that is equal to 4 in this case. Next we'll move on to the 11th question. Now we have the 11th question. 11th question is a star is a binary operation on given set. The set is a Cartesian product of the set of natural numbers, so it is n cross n. And what does the operation say? That one ordered pair, when it is operated with another ordered pair, you get in this way, that is first plus first, second plus second. Okay, that's what you are going to get. So the question is to find whether it is commutative, associative, and also does it have an identity element in this case. Okay, so first we'll take for commutative. This is commutativity. So we'll take a comma b star c comma d. A comma b star c comma d comes to be a plus c comma b plus d. Okay, then what is c comma d star a comma b? Yeah, you are not going to take everything as a reverse. Here the second element comes first for commutative, that's what it is going to be. So this comes to be c plus a and d plus b. They are equal, right? This a plus c and c plus a, they are same. B plus d and d plus c is same. So it is commutative. So now we are going to have for associative. For associativity, it should be a comma b star c comma d star e comma f. This is the first one. Second one is a comma b star c comma d star e comma f. You need to check whether these two are equal. If it is equal, then it is associative. Okay, now this with this, that is the first element of this plus the first element of this comes to be a plus c. First element of second of this and second of this you need to add. It is b plus d star e f. Okay, now we have again this is the first, this is the second. So first of this plus first of this, that is a plus c plus e, and second of this, so b plus d plus f, b plus d plus f. So this is this one. So we need to check how we are going to get it here. This is a b star c comma d star e comma f, that is first plus first, that is c plus e, and second plus second, that is d plus f. You are going to get. Again you have first plus first, that is a plus c plus e and b plus d plus f. B plus d plus f. This you can observe that these two are equal, right? They are equal. Therefore it is associative. Next we need to find whether it is having some identity element. I'll rub these two parts for that. Okay, I'll rub only the commutative part. Since it is commutative, it can have a chance to have an identity element because both are the same, right? Identity. So it should be a b star c d is equal to ab. I am considering let cd be identity element. identity element. Okay, this is one step I need to write first here. So after writing that, I can write the statement that is a comma b star c comma d is equal to a comma b, that is equal to c comma d star a comma b. I'll just rule out because this is a commutative, so both the conditions sum up to the same condition, so I can just rub off this part also. Okay, now we have this condition. Here you have a, the first plus first, a plus c, second plus second, that is b plus d, that is equal to a b. So if it is an ordered pair, both the ordered pair should be same, the abscissa as well as the ordinate should be the same, that is a plus c is equal to a and b plus d is equal to b. B and B is going to be cancelled, A and A is also going to cancel, because C is equal to 0, D is equal to 0, therefore C comma D is equal to 0 comma 0. Now we have the set A, we need to check whether it is going to be belonging to that set A. The set A is the set of Cartesian product of the natural numbers. Natural numbers includes 1, 2, 3, 4, it doesn't have 0. So this does not belong to A. Therefore no identity element exists. No identity element exists. Okay. Next we have the 12th question. Now we have the 12th question. 12th question is all about just to tell whether it is true or false and just justify that. So the first one is, it is given that for any arbitrary binary operation star on the set n, a star a is equal to a for every a that is belonging to n. Right? This I think it is not a correct statement. So let me take, say, an operation like this. Let a star b is equal to ab. Let a star b is equal to ab. Then a star a is equal to a square, that is not equal to a always, for every integer, for every a that is belonging to n. This is just a counter example. Therefore the statement is not always true. Statement is not always true or is false. There may be some conditions maybe where it is going to be satisfied, but in this case I am taken an example. It is not always true, right? That's what you're going to tell. The second part of the question is all about if star is a commutative binary operation on the set n, then a star b star c should be equal to c star b star a, right? It is given it is commutative, right? If it is commutative, then we need to check whether this is correct or not. So let me take the left hand side, that is a star b star c. If it is commutative, I can just interchange these two, right? So this comes to be a star into c star b. I just interchange this. So now you consider this as one element and this as one element. Again, it is, since star is commutative, you are considering this star now. I am going to interchange these two. It comes to be c star b star a. That is this RHS. That is this RHS. Therefore the given statement is true. Okay. Now we are going to the 13th question. 13th question is a simple one. It's an MCQ question. It is given a star b is equal to a cube plus b cube. The options just say whether they are commutative, associative or not. That's it. Okay. So just we are going to check whether it is associative or commutative and such things. Only that much. So first we are going to take commutative. For that a star b should be equal to b star a, that is a cube plus b cube, and this is also b cube plus a cube. They are equal, right? So it is commutative. Now we are going to take the associative nature, that is a star b star c and a star b star c. Okay, let me take this two. This becomes a cube plus b cube, and this is one term, and this is c. This is a star b cube plus c cube. Okay, Now this is first cube plus second cube. That is a cube plus b cube whole cube plus c cube. And this is a cube plus b cube plus c cube whole cube. That's what the first term cube plus the second term cube. That's what it means. So just by seeing you can understand that they are not going to be equal, because here you have a cube whole cube, that is a raised to 9. Here there is no term of a raised to 9. Therefore it is not commutative. The option which says that it is commutative but not associative is all about option B. Option B is the right answer. Next we'll go on through some miscellaneous examples and then go to the miscellaneous exercise.